Hello everyone. Now look into another sorting algorithm called insertion sort. Now this is the simplest of sorting of all algorithms, and the way it works, it's the very similar way that we sort the playing cards. Okay. Now let us have one small example based on this. Let us say we have an array consisting of 6 elements or 6 numbers stored at index 0, 1, 2, 3, 4 and 5. So what we'll doing in this, in the first phase, we'll compare elements stored at index 0 and index 1. We are trying to create or sort this array in ascending order. So we'll check whether the element stored at index 0 is less than index 1. Yes, it is less. So we'll add 14 to the virtual subarray, and this is what we said to be a sorted subarray or sorted list. And rest we will consider these are in the unsorted list. So in unsorted list we are having 34, 28, 12, 38 and 20. Now in the second phase we'll check elements stored at index 1 and index 2. We'll compare upon this. Is 34 less than 28? No, that means position of 34 is not proper. So what we'll do, we'll swap it. So we'll add 28 to the sorted list. Okay, so in the sorted list you are having 14 and 28. Now we'll first check whether the position of 28 is proper. So we'll check with this previous number. Previous number is 14. 14 less than 28, it's proper. That means now we are having in unsorted array we are having 34, 12, 38, 20, and sorted order we are on sorted part we are having 14 and 28. So this is proper. Now we'll go on the third phase. In third phase we'll check upon elements stored at index 2 and index 3. At index 2 we are having 34 and index 3 we are having 12. So is 34 less than 12? No. Then we will swap it. So this will become 12 and this will become 34. So 12 will get added to the sorted part. In the sorted array we are having 14, 28 and 12. Now we'll check upon whether 12 is at proper position. So we'll check upon with previous value. 12 is at right now index 2. So we'll check with index 1. So 28 and 12, are these proper? No. So we'll swap it. So we'll get 12, 28 and here 14. Now process continues. Now still we are having the newly added number is 12. So we'll check with the previous number. So 12 and 14, is 14 less than 12? No. So again we will swap it. So 12, 14, 28. So this is the actual sorted list, and the unsorted list now still consists of 34, 38 and 20. So this is the end of your third iteration. Now you are going to the fourth iteration or the fourth phase. Now in fourth phase you will compare the elements stored at index 3 and index 4, that is 34 and 38. Is 34 less than 38? Yes. So we'll add 34 to the sorted list. So you'll have 12, 14, 28 and 34. So now we'll first check 34 with its the last member of the sorted list. So 34 and 28. The position of 34 and 28 is proper. 28 is less than 34. So now we focus on non-sorted list. So non-sorted list consists of 38 and 20. Now the fifth iteration. In fifth iteration you are going to check the next two elements. Those are nothing but at index 4 and index 5. So 38 and 20. 38 is less than 20. So we are going to swap it. So 20 followed by 38 and 20 gets added to the sorted part. So you are having 12, 14, 28 and 34. Now as 20 is added to the sorted list, so then we'll place 20 at a proper position. So we'll press check 20 with its previous element, that is 34. Is 34 less than 20? No. So we'll swap it. So this will become 20, this will become 34. Other elements are 12, 14 and 28. Now we'll check 20 with its previous. Previous is 28. Is 28 less than 20? No. Then we will swap it. So this will become 20 and here we will get 28. Rest elements 12, 14 and here 34. Now we'll check 20 with index 1. At index 1 we are having 14. Is 14 less than 20? Yes. That means the newly added element 20 or the newly added number 20 is at proper place. Then we are having at the end of the fifth iteration, the sorted list consists of 12, 14, 20, 28 and 34, and the last element is 38. So now at the sixth iteration, that final iteration, as there is only one number, that means this number is at a proper position and this number gets added to the sorted list. So at the end we will get 12, 14, 20, 28, 34 and 38. So that's how basically this insertion sort algorithm works. However, we cannot use this insertion algorithm in the case we are having a huge data set. We can use it only in the case we have data very much less. And the main reason behind is that what do you say, that time complexity and space complexity. As far as time complexity is concerned, we can get the best complexity of order n. This is possible if and only if the list itself or the numbers are already arranged in sorted order. Whatever the array we have, whatever the numbers we are having, those numbers are already in sorted order. Then and only we can get the best time complexity or best case complexity of big order of n. Else, for average and worst case, time complexity is of order of big O of n square. Okay, so that's the reason why we basically do not use this insertion sort algorithm. As far as space complexity is concerned, for space, every time we are requiring, we are just swapping it. We are not taking any additional memory space. But to swap two numbers or interchange two numbers, we always take one extra variable. So in that case, we can say space complexity of this algorithm is big O of 1. So that's it for this session. In the case you have liked, kindly hit like and subscribe. Thank you.